That's right. On the Earth's surface, the acceleration due to gravity is 9.8 meters per second. And do we understand the difference between the acceleration due to gravity and the gravitational force? Hopefully we understand the difference between those two, right? Acceleration is meters per second squared. That's how fast our velocity is changing. Gravitational force takes mass into account there. Okay? So now we're going to start with our original equation for the force due to gravity. And we're going to manipulate that to allow us to solve for the gravitational acceleration, or the acceleration due to gravity, at different points above the Earth's surface. Okay? So we're starting with our original equation here. This is the one that you got yesterday. Hopefully we recognize that a little bit. Mass of the Earth is going to be one of the masses that we're working with. Okay? You don't need to write down this whole derivation of equations. I'm just going to walk you through how we get to this last one, which is the one that we need. Okay? So since we're looking at the gravitation of the acceleration due to gravity around the Earth's surface, or at the Earth's surface, or a little bit away from the Earth's surface, whatever, we're looking at the Earth. So mass of the Earth needs to go in there for one of the masses. Now we're substituting mass times acceleration due to gravity for Fg. Okay, remember how we talked about last class, there's two ways you can solve for the gravitational force. This way is one, and then mass times 9.8 is the other one. Right? Does that ring in a bell? So now we're going to substitute mass times g, which is the acceleration due to gravity, right? Most of the time it's 9.8 when it's on the surface of the Earth. When we are not on the surface of the Earth, we might have a different acceleration due to gravity, right? So we're substituting that. Why are we using m2 here instead of mass of the Earth? We're looking at the acceleration due to gravity, yes, but we're not talking about the mass of the Earth here. We're talking about the mass of the object, whatever object we're looking at, right? Yeah, we're going to end up canceling it. That's right. Okay? So now we are going to be able to cancel m2 on either side, right? We're going to be able to get rid of m2. So we say m2 and get rid of that, which leaves us with the acceleration due to gravity is equal to big G times mass of the Earth over r squared. What do we know about this r value? What is it always the distance from what to what? That's right. So if I'm talking about, the acceleration due to gravity on top of a mountain on the Earth, hey, that looks like a party hat on something. So if we're up on top of a mountain and I'm talking about what's the acceleration due to gravity, I'm going to find the radius from the center of the Earth to the top of that mountain. Okay, so this would be the radius of the Earth plus whatever this height is of our mountain. That makes sense? That would be the radius I would plug into this equation here. Okay, and what does radius always need to be measured in? Meters. Good, not kilometers, meters. I want to solve for gravity at the Earth's surface. Okay, and I want to see if we can get it to come out. What would we be expecting gravity to be at the Earth's surface? 9.8. So let's solve for it. Let's see if it works. Okay, so we'll use g times mass of the Earth over r squared. Okay, and we're going to see if this truly comes out to be 9.8. Okay, so go ahead and get your calculators out if you don't have those already. So I want you to plug this in. Big G is equal to... Perfect. 6.67 times 10 to the negative 11th. The mass of the Earth is 5.98 times 10 to the 24th. And what radius are we going to be dealing with here? Anything extra beside the radius of the Earth? No, because we're looking at the Earth's surface. Okay, so we're just going to say 6.38 times 10 to the 6th, and then we square that whole radius term. We proved here that the acceleration due to gravity equals 9.8. So whenever we're solving, that's right, 9.799. When we solve for little g, our units should always be what? Meters per second squared, right? So when we're solving for Fg, our units are newtons. When we're solving for little g, our units are meters per second squared. Okay, be careful about that. Would we be expecting the acceleration due to gravity to increase or decrease as we get farther away from the surface of the Earth? Decrease, right? That's why when you go to the moon, right, the acceleration due to gravity on the moon is only 1.6 meters per second squared. Okay, it's about the 10th or whatever of what it is on the surface of the Earth. So as we get farther and farther, you'll see a little bit of a drop in gravity, right? When you climb Mount Everest, I don't think you're going to see things floating yet, but you're going to have a little bit less of a acceleration due to gravity acting on you, so you might be a little lighter there. Okay. All right, so let's try and find the acceleration due to gravity on the top of Mount Everest. You can solve this radius separately and then plug in that sum. That's fine, right? I just put it all into one equation. You can do it separately. That's fine too. Something that you should think about when you are adding these, though, is don't round it again. Because when you see you do that in your calculator, 6.38 times 10 to the 6th plus 8,848, it would just round to 6.38 times 10 to the 6th, right? You have to keep those numbers in your calculator. Don't round it, or it's not gonna make any difference. Okay, so in these problems, especially when you're solving for the acceleration due to gravity, you want to be as specific as you can, because the difference between 9.8 and 9.67 is not that great, and it could be a rounding thing, and you won't be able to see that difference in your calculator. Okay. Okay. What'd you have, Manny? 9 point. Don't round so much.
7.
One more.
7.
Yeah. There we go. Okay. So especially for these gravity, acceleration due to gravity, I want you to keep it out a few decimal places. Because if we round, again, it doesn't seem like we have any difference, right? But there's the slightest difference when we get to the top of that mountain. So it's going to be a pretty small differential that you'll see here when we're talking about the acceleration due to gravity. And this, realistically, is barely off the surface of the Earth, right? Even though it's 8,000 meters above sea level, that's barely any distance when we're talking about the magnitudes of that gravitational force. So we want to keep as exact as we can. All right, and our units here are meters per second squared. Okay, questions here? All right. Okay. Now we're going to talk about satellites and how they orbit. And these are specific equations for satellites orbiting the Earth. Okay? So you might put satellites on your equation sheet for this one. Okay? Right here? This is pi. Okay, here's the Earth. Kind of just looks like a button. Anyway, when we have our satellite out here in orbit, our satellites realistically stay the same distance from the Earth through their entire orbit, right? It's not a zigzag pattern that they're getting closer to the Earth and farther away from the Earth, and that's not what we're looking at here. These satellites should realistically have a very uniform orbital or uniform circular path around the Earth. What do you think it is that holds that satellite in its circular path? Gravity, right? The Earth's gravitational force is holding that satellite just enough in that circular path. So we're going to combine here our kind of equations for uniform circular motion along with our gravitational force equations. Okay, and that helps us look at the period of this satellite, right? How long it would take to orbit the Earth. It helps us look at a lot of different things. Okay, so when we talk about satellites, we need to think about them orbiting at the same height or being in a uniform circular path around the Earth. Okay, so if we want to find the speed of a satellite orbiting around the Earth, this is the equation we would use. Again, this is specific for a satellite, so I might put that on my equation sheet. These are satellite equations, okay, because they combine circular motion equations with gravitational force equations. Okay, and then if I want to find the period of a satellite, remind me what period means. Good. Time around the circle once. Okay. So period is the time it takes to revolve around that circle or complete its orbit or whatever you want to say one time. Okay. This one's tricky. We see an r cubed here. Okay, radius cubed. I can walk you through how this equation comes about, but I don't want to, and you don't want to, so I'm not going to. Okay, this just trust me. Okay, or you can look in your book if you want. It probably has it in there. It's not really necessary, but you can see where it comes from if you would really, really like to. All right. What would period usually be measured in? Usually seconds. Yeah, good. Okay. Let's try it. Oops. Assume a satellite orbits at a height of 225 kilometers above the Earth's surface. That's a big key for us here. Above. Okay. What's the satellite orbital speed and period? We don't need to know the mass of the satellite, right? That didn't go anywhere in our equation. Just the mass of the Earth was in our equation. Okay, so we don't need our mass of the satellite at all. Okay. So we have a radius here. 225 kilometers. Is that going to be our radius? No. What should we do to that? Not quite. Not yet. We want our radius to always be from what to what? That's right. We want it to be from the Earth's center to our second object. So if we have our Earth and here's our satellite, right? The radius of this is where we want our radius to be, from the center of the Earth all the way to that satellite. Okay? This is a distance of 225 kilometers. So what should we do here? Add it to the radius of the Earth, but first we need to put that into meters. Okay? So that's going to tell us 225,000 meters plus 6.38 times 10 to the 6th. That would be our radius. That is something that you will need to identify with and be able to do pretty often, right? Anytime it says above the Earth's surface, we got to be thinking about, we got to have the center of the Earth all the way to that object. Okay. So that gives us a value of 6.605 times 10 to the 6th. All right, we want to solve for the speed of our satellite, so we'll use v equals square root of g, mass of the Earth, over r. And this r is not squared. Bless you. Oh, that's just how the equation works out. When we would take the equation to rearrange and solve for velocity, it gets rid of the square root.
What does G stand for?
Which one? Big G?
Yeah, the G.
G is the universal gravitational constant. That's the 6.67 times 10 to the negative 11.
I'm confused on why you use the 6.67 and 5.9.
Right here.
Yeah.
Because this is big G, which is our universal gravitational constant, and this is mass of the Earth.
Oh,
So those are just part of the equation.
so you would use it every time for that.
Yeah. Yeah, this is set equation. So it doesn't matter what the satellite weighs. It doesn't matter any of that. It has to do with the combination of that circular motion equation and our gravitational force equation.
It is always in second.
Uh-huh. Yeah. Yeah. You mean the algebra part to get the answer? Yeah, sure. Okay, so I like to start from the bottom right here, and I'll kind of work my way out of it. Okay, because I like to keep everything in my calculator. So in my calculator, I put G, 6.67 times 10 to the negative 11th, times 5.98 times 10 to the 24th, and then I hit enter. And that gives me this denominator right here. Okay, I don't need to, you can rewrite that number, I don't care. Okay, so then I'm going to plug in my numerator, 6.605 times 10 to the 6th, and then I'm going to hit math, and I'll cube that whole thing, and I'm not going to hit enter yet, because then I'll hit divide by second answer.
If you don't put the parentheses in there, will it mess it up?
Well, I use the E button, so that parentheses, I don't need parentheses. If you use that EE button.
I got a completely different answer.
Okay, did anyone else get this answer, or did I plug it in wrong?
Okay, wait, I got that.
Okay.
When you say plug in second answer, how did you get the second answer along with it?
Oh, I mean like on the calculator I hit the second button, and then I hit answer. That's fine. Okay, Mary, are you on the same page so far?
Yeah.
Yeah? Okay, so after I hit answer and divided by my denominator, then I hit enter. And that gives me about 722,422. Yeah? Okay, then I'm going to hit second square root, answer. Right? And that'll give me 849. That's the whole square root term right there. Yeah, did you get about 849?
Yeah.
Okay, and then we hit times 2 times pi.
Oh, okay.
Okay? So I like to start at the bottom and work my way out because I can usually do that in my calculator without having to reset anything. Okay? Yeah, you can plug it in at one time, that's fine, but
Give you 3.19.
okay. I drew a lovely diagram here of the Earth and the satellite. Okay? So what it's saying is as the Earth moves, the satellite moves at the same rate. Okay, so if the Earth rotates, the satellite rotates at that same speed. Okay, not the same speed necessarily, but if the satellite was shining down a light on the Earth, that light would never leave that location because the satellite's going to move with the same kind of angular momentum or angular velocity, as the Earth is. Yeah, well, the moon's not always at the same location in reference to us on the Earth, right? The moon stays in one, right? We can't see the moon in the same spot. Yeah. But we have to understand, like, if there was a satellite above Topeka, we would be able to see that satellite 24 hours a day, 7 days a week, all the time, because it's always at the same kind of longitude and latitude coordinates pointing down. Does that make sense? Okay, so if the Earth is rotating and the satellite is a farther distance out, that means that satellite's going to have to be moving at a much greater velocity, right, to cover that much more distance than the Earth. But the period is the same, right? It takes the same amount of time to get around. It just has a greater distance as traveling. Yes? No? Okay, good. All right. So first of all, we have to find out what is the period of the Earth. Right? How long does it take for the Earth to make?
24 hours.
Yeah, 24 hours. Okay? To make one complete spin, it takes 24 hours. We're not talking about around the sun here. We're talking about one spin. So do we usually want our period in hours? No, we want it in seconds. Okay? So to convert from hours to seconds, 1 hour is 3,600 seconds. Okay, or 60 minutes and 60 seconds. Okay, and our goal here is to find the height. So that's the radius, right? We want to find the height above the Earth's surface. And this part makes a difference here, and we will look at that at the very end of the problem, okay? But we want to find the height above the Earth's surface. So right now we saw that our Earth was here. Our satellite was in orbit out here. But the radius that we solve for will be from the center of the Earth all the way to the satellite. Okay, so at the very end, what do we think we're going to have to do after we solve for this whole radius? That's right, exactly. We want to subtract out the radius of the Earth so as to just get this distance. Okay, that'll be at the end of the problem, and we'll talk about that again, but I want you to have that in the back of your mind. Okay, does that part make sense? All right. So we want to solve for the radius using the equation for period of a satellite. So T equals 2 pi square root r cubed over GM Earth. Okay. We know the period, we know 2 pi, we know g, and we know the mass of the Earth, so we're solving for r here. Okay, so algebraically this is going to take a few steps. What do we think our first move algebraically should probably be?
Divide the 2 pi over.
Exactly, divide that 2 pi over. So now in your calculator, you need to be very careful. 86,400 divided by 2 divided by pi, or 86,400 divided by parentheses 2 pi close parentheses. Okay, if you do not do that, if you just do 86,400 divided by 2 times pi, it's going to take it divided by 2, then it's going to take that whole answer times pi. Okay, so when you do this in your calculator, you need to either put parentheses around that 2 pi, or you divide by 2, divide by pi. Okay, yes, clear? 86,400. A lot of you will forget to do that. I'm just telling you right now. Okay, that gives us 13,750.98 equals square root of r cubed over, what's the product of that? Perfect. 3.9. I'm just going to round that 3.98 times 10 to the 14th. Okay. From here, what's our next step algebraically?
Square.
To square both sides. Good. We want to get rid of that square root. All right. I'm going to get rid of some of... Can I get rid of some of this? Hopefully. So I'm going to square both sides, and I'm going to move it up to the top right here. 13,750 squared. Okay, so 1. You don't have to rewrite all this while you're doing this, but I'm just showing our whole algebraic step here because this one's tricky. Okay. From here, we're going to multiply that by 3.98 times 10 to the 14th. So we multiply those two things to get r cubed by itself. Okay, and then in our calculator, we need to do a cubed root. We're going to hit math, go down to number 4, cubed root of second answer, which means r equals 4.22 times 10 to the Okay, is that our final answer here? No, it is not. Okay, so to finish our problem, since we want to know it above the Earth's surface, finish our problem, we subtract out the radius of the Earth. 6.38 times 10 to the 6th. Okay, so I want you to go ahead and find the speed for that satellite. When we find this speed, are we going to use the radius, that our final answer from the last problem, or are we going to use the total radius? The total radius, right? So we can't use that 3.58. We want to use the total radius here, from the center of the Earth to the satellite.
Oh, you finished with that?